All right, let's look at this relationship between the roots of a polynomial and the coefficients of the polynomial. We've seen the idea already, of course, in quadratics. Let's say quadratic ax squared plus bx plus c, and we saw that, oh, well, yeah, the sum of the roots minus b on a, the product of the roots c on a. So it's that sort of idea, but we're going to extend it through to any polynomial. So if I have a cubic, so the general one becomes ax cubed bx squared cx plus d, turns out the sum of the roots is still minus b on a. Does not change. But notice b is now the coefficient of x squared, not the coefficient of x. And so you always start with the leading coefficient being a, and if you do it that way, it's always the same. So you get minus b on a. The interesting one is the product of the roots. We don't call it the product of the roots anymore. We call it the sum of the roots two at a time. So it's all the possible products. You could have alpha with beta, you could have alpha with gamma, you could have beta with gamma. But that will still be C on A, because now there'll be a third one, which we could call the product of the roots, alpha, beta, gamma. That will now be minus D on A. So the pattern, as you'll notice, that the coefficients are just going along nicely, B, C, D, but the signs are alternating. So minus, plus, minus, and so on. So if we had a quartic, so now it'll be ax to the 4, and our constant term would be e, the sum of the roots one at a time will still be minus b on a. Two at a time, and there's 6 possible pairings there, will be c on a. 3 at a time, 4 possible ones there, minus d on a. And now we'd have 4 at a time, that would be e on a. By the way, there were 4 when we did 1 at a time. There were 6 when we did 2 at a time. There were 4 when we did 3 at a time. What's the significance of that? It's combinations. Yeah, exactly. Because what you're basically saying is, if it's 2 at a time, we're saying how many ways could we choose 2 of the roots from 4 roots? So 4c2. Which is 6. So that's how you could always tell. Oh, how many possibilities would there be? So if I had after a quartic, the next one we would call a pentic. That would be one name, pent being the prefix. So if we had a pentic, and I wanted to see how many, well, let's say 3 at a time, how many possibilities would there be? It would be 5c3, whatever that works out to be. All right, we can generalise this through then. So if we've got any polynomial, so a will always be the leading coefficient, down to whatever the constant is, however many we've got. The shorthand way, rather than, if you've got a long one, it certainly helps, rather than writing alpha plus beta plus gamma plus delta plus epsilon plus, keep going, you can use our sigma notation for sum, and then we just write the first root down. But that's basically saying I want the sum of the roots 1 at a time. And that'll always be minus b on a, regardless of the degree of the polynomial. So the sum of the roots 2 at a time will always be c on a. Sum of the roots 3 at a time will always be minus d on a. Sum of the roots 4 at a time will always be e on a. I didn't bother keep going from that. But 5 at a time would then be minus f on a. 6 at a time would be g on a, and so on. So that pattern just keeps going. Now, you may remember this idea when we had to find the sum of the roots squared, the alpha squared plus beta squared, and we played around with the perfect square. That pattern also exists for all of them. So sum of the roots 1 at a time squared will always be the sum of the roots 1 at a time squared, the pause there was important, minus 2 times the sum of the roots 2 at a time. Yeah. So that will always be true. So I got a cubic. For some insane reason, we want to know what 4 alpha plus 4 beta plus 4 gamma minus 7 alpha beta gamma is. I'm sure it's a very useful relationship for someone, but anyway. Well, we know alpha plus beta plus gamma is 5 on 2. You might be thinking, well, why is he bothered working out 2 at a time? Well, probably because if this is A, there's going to be other questions where that might come in handy. So I may as well just work out the 3 basic ones, and there's alpha, beta, gamma. It'll be minus a half. So if I sub in Well, it's just simple substitution. 4 times 5 on 2 minus 7 times minus half, 27 on 2. There it is. The reciprocals, another common question they like to ask. Well, we just treat it like an algebraic fraction. Let's put it all together and we see, oh look, all I got on the top of the fraction, sum of the roots 2 at a time over 3 at a time. So we'll sub in what we've worked out for that. And we get positive 3. We get positive 3. Let's do the square one. So as we've seen, look, this is where sum notation's handy. Rather than having to write all that out, I could have just written sigma alpha all squared minus 2 times sigma alpha beta, a lot quicker. But subbing in, and we get 37 on 4. So very similar questions to what we saw with quadratics. Oh, there's that year again, 1988. I keep telling you, it was a good year. You would have loved it. It was a fantastic year. The roots of x cubed minus 3x plus 1, and they were very generous for part I. Find alpha plus beta plus gamma. If anyone in the state got this one wrong, oh boy, oh boy. But you know what they're going to have done, don't you, if they got it wrong? Because look at it carefully, there is no x squared term. So you can see people working through this very quickly, but actually the answer is 0. I would imagine there would have been a lot of people, well maybe not a lot, but there certainly would have been people that wrote down the answer of 3 for that one. Yeah, so be careful. Okay, part 2, they're still generous. Alpha, beta, gamma. Just in case you didn't get part I, oh well, let's give you a gift in part 2. Okay, that one's negative 1. Now, part 3, the standard reciprocal question. You see the same questions coming up a lot. So all right, create our algebraic fraction. Let's sub in what we've already worked out, which nicely we've done in part I and part 2, so we've already got those. And, oh no, negative 3 on negative 1, which is, negative 3. Oh, phew. Okay, positive 3, of course it's positive 3. Why were we even worried about that? Okay, here's one a little bit more recent, although now it's still getting to be quite a few years ago. 2003 paper. So it's known that 2 of the roots, try that again. It's known 2 of the roots of this particular equation, they're reciprocals of each other. We've got to work out what k is. Well, if they're reciprocals, instead of calling them alpha, beta, gamma as the 3 roots, I'm going to call them alpha, 1 on alpha, and beta. They're going to be my 3 roots. We've got to find the value of k. All right. Well, I can work out beta straight away if I play with the product of the roots, because that's the beautiful thing about reciprocals. Of course, when you multiply them together, you get 1. So I'll do that. So I actually now know one of the roots is negative 3. That now gives me 2 ways I could go and find the solution to k. I could simply say, well, hang on, if negative 3 is a solution, I'll use my factor theorem. Sub in negative 3, it should give me 0, and eventually, there it is, k is 13. Did I put the other way of doing it in there? Did I bother with it? Okay, the other way, of course, would have been, well, k's in the second last term, so I could have played around with the sum of the roots 3 at a time and come up with an equation to solve, and that probably would have been longer, I would imagine, but it's another way you could do that. Sorry, did I say 3 at a time? 2 at a time would have been for a cubic, wouldn't it? That second last one. All right, 2006, we have a cubic. K, R, S and T. R, S and T are real numbers. It has 3 real zeros. And you might be wondering, why do they keep throwing this word real in there? But don't worry, soon we'll understand why. Okay. So 1 is definitely a solution, and then the other 2 solutions are like opposites. One's positive, one's negative. Find the value of the pirate. Okay. We know the sum of the roots, 1 at a time. In this case, that's a good one to use because the alpha and the minus alpha is going to cancel. We know that's minus r. You can't help yourself, can you really? So, r is negative 1. Okay. Next part. Find the value of s plus t. Well, we know what R is. All right, let's look at 2 at a time. That's got S. What happens there? Oh, we've got a whole heap of things cancelling. Alpha minus alpha. So I know S is minus alpha squared. Okay. Do 3 at a time. Let's see what that gives me. Oh, hang on a sec. Now that makes it rather handy. T turns out to be alpha squared. So now I know that S plus T is 0. All right. And my alternative was, of course, well, again, it was similar to that last question, isn't it? I know minus 1 is a solution, so again, I could just sub in and we end up with S plus T for that. And that gets 0 as well. So, yeah, you just play around with the algebra. That's the fun part of it, I guess.
Yeah,
Alrighty.